process. So when you see a reaction, you need to start looking for the individual pieces within it and try and decide what can happen and how things overall occur. So when we look at a substitution reaction, how can you tell that a substitution occurred?
Something taking its place.
Something's been swapped out. Okay, so most people tend to look or find that substitution part very quickly. You've got the leaving group versus the LG versus that nuke bond exchanging. Remember, your reactions may not always be balanced, so you can't trust that necessarily. You may see some other bonds kind of shuffle around, and we'll talk about those when we encounter them. With the substitution reactions, we've got 4 primary components to worry about: your substrate, your leaving group, your nucleophile, and your solvent. It was last Wednesday we went through and talked about, I'm pretty sure, just the substrate and the leaving group, and we hadn't quite gotten into nucleophile or solvents. Okay, so that's pretty much where we're going to pick up today. Any questions about your substrates or leaving groups? Okay. So, solvents. Look at that, I was right. We need to come up with some way to classify them. So when we're looking at our solvents, it's kind of an odd relationship. We typically only see them in lab when we actually have to choose and pick them out and put them in. Okay? So when we look at them within our individual reactions, they play a much smaller role. You could probably get away with completely ignoring solvents altogether and still getting through most of this class and most of the final without having to stress about identifying them. Okay? They have a couple roles that they play. Our primary role is to try and get everything mixed into one phase. So when we look at the substitution reactions, we'll slide back one, you'll notice we had that M versus H up with the nucleophile. If it's an M, what did M stand for? Metal. So we're looking at a metal bound to a nonmetal. Our nucleophiles, this being organic chemistry, will all be nonmetals. What kind of bond is that? It's an ionic bond. What kind of solvent might be important for an ionic bond to dissolve in? It's going to need to be polar so it can stabilize those charges, that positive and the negative. So when we're looking at substitution reactions, our solvents will all typically have to be quite polar to help stabilize that nucleophile so that we can get through and process the experiment as best we can. Okay? That secondary role is looking then at how it interacts with the individual reagents. So our primary was just to get everything into that same phase, get it to dissolve. Then the secondary is what specifically does it do? Okay, because maybe in the process of looking at that solvent properties, we might end up finding that it stabilizes particular intermediates, which could be good. Okay, that could facilitate the reaction going faster. Or it could destabilize particular reagents or intermediates, and that could actually ruin the reaction. So we have to be careful when we look through at those secondary conditions, and that's primarily where we're going to be focused. But before we can even get into that effect, we need to come up with some classifications so we can refer to them pretty cleanly. So what might be some classification terms that we could use? Heard one pop up already. What kind of solvent do we want for an ionic compound? Polar solvents. Okay. What's another classification based on that? Nonpolar. So we have a polar versus nonpolar solvent situation. How might we identify if our solvent is polar? Look at the bonds present within that solvent structure, and if we have polar covalent bonds, we would expect a polar solvent in most cases. Okay? Does it have to be just polar covalent? Are we going to, or sorry, just polar? Are we going to have gradations off of a polar solvent? Okay, so said another way, if we look at our intermolecular forces from a polar covalent bond, do we only have one type of force? No, we have both the dipole-dipole force, which is a polar interaction, and we also have hydrogen bonding. Hydrogen bonding is a stronger dipole-dipole, which is going to mean we end up with a larger pole. Okay, so we need to add an extra classification within our solvent system to account for the ability to hydrogen bond. Because if hydrogen bonding is present, we now have a much stronger interaction or a much more polar molecule, and that could change our reaction dynamics. Okay? So we've got our polar and nonpolar, and we're looking at that hydrogen bonding interaction. Okay, we could call it a polar hydrogen bonding solvent or a polar non-hydrogen bonding solvent. It gets a bit tedious. What do we shift to? Protic versus aprotic. Protic for a proton, which would be coming from our hydrogen in our hydrogen bonding solvent. So if we take a look at our classic hydrogen bonding solvent, we've got water. What type of bonds do we have in water? Careful. What type of bonds do we have in water? We have polar covalent bonds, which lends itself to dipole-dipole forces, which we can then further classify as hydrogen bonding. Why is hydrogen bonding considered such a strong force? The electronegativity difference between our oxygen and our hydrogen. So it's the strength of that dipole. Our hydrogen generates a really big partial positive, and our oxygen generates a really big partial negative. Well, if our hydrogen starts to become positive, it starts to look like a proton, hence our protic versus aprotic. So our protic solvent really is just a fancy way of saying it's a hydrogen bonding solvent. Okay, and our aprotic situation just means that we don't have hydrogen bonding. You'll notice that we'll really only refer to protic and aprotic under the polar categorization. Why not subcategorize our nonpolar? Our nonpolar has no ability to be able to give up hydrogen or hydrogens. It cannot hydrogen bond. Why not? It's nonpolar. We're looking at covalent bonds, which only means London dispersion forces. We can't be a hydrogen bonding solvent. Why don't we call it nonpolar aprotic? It's redundant. Okay? If it's nonpolar, it's by definition going to be aprotic. Okay? So when we're looking at our solvent classifications, it's really narrowed down to three: nonpolar, polar aprotic, and polar protic. Okay? Is that a question? No. Okay. So those are going to be our primary classifications when we're looking at our solvents. We now need to understand something about them and being able to identify them. Okay? So let's take a look at a couple solvents. Okay? These have been used in a variety of different cases. The only one we probably won't see in the lab would be benzene. You've already seen methanol, DCM, acetic acid. We might encounter DMSO, but even that one's a little bit questionable. Anybody know why DMSO is typically not seen in the labs, at least undergraduate labs? It soaks through your skin. It was actually originally thought to be used as a non-hypodermic needle way of getting stuff through your skin barrier. So you can mix, one of the classic ones is mix a little bit of spearmint with DMSO and then put it on your skin and you'll taste it instantly.
Taste it?
Yeah.
On your ear?
It pumps directly into your bloodstream that fast. So that's one of the primary reasons we don't allow students to play around with that, because that pretty much drops stuff immediately into your bloodstream, and that can be a bit problematic, particularly when we're dealing with insanely toxic chemicals. It does have some other decomposition products that aren't exactly pleasant as well, but that's one of our primary concerns with it.
Is it bad to get the DMSO in your bloodstream?
It's not good.
Okay.
So that's like chewing gum 2020, right?
Yeah, there you go.
Does it freshen your breath?
I don't know that, actually. That could be an interesting idea.
It sounds like we've got an idea.
Well,
Yeah.
you guys can work on that at some point later. That's actually looking at the reverse, being able to spit it back out. I don't know. Beside the point, let's go back to our solvent classifications. How would we classify these solvents? So we got the three primary classifications up top: polar protic, polar aprotic, and nonpolar. Okay. So spend a little bit of time, talk with each other, and get those nailed down. Hopefully you can come up with that pretty quickly. Topic. Benzene. I look at benzene and I see a bunch of hydrogens in there, which means I got a hydrogen bond, right? So that should be polar protic. Why not?
It's bonded to carbon.
Just because we have hydrogen doesn't mean it's hydrogen bonding. Remember, hydrogen bonding is a force. It is not a bond. So when we look at that structure, we have bonds between hydrogen and carbon, which is a covalent bond, London dispersion forces, nonpolar interaction, and what we end up with would be our nonpolar classification. So I'd just probably write N for that. DMSO, also known as dimethyl sulfoxide. The sulfoxide is referring to your sulfur and oxygen double bond, and then you have two methyls attached to it, hence your dimethyl sulfoxide. What do we think? We're looking at polar aprotic. We again have those hydrogens, but what are those hydrogens attached to? Carbon, so they're not protic. So we're looking at a polar aprotic solvent. Right, just like we already kind of talked about with DMSO's kind of safety issues, it does a really good job dissolving things, which is one of the reasons why it typically gets used a lot. Methanol, we're looking at a polar protic solvent because we have a hydrogen bond bonded to oxygen, nitrogen, or fluorine. In this case, it's oxygen. We have a hydrogen bonding solvent that's going to be polar protic. DCM, which refers to dichloromethane, also known as yes, it's also referred to as DCM. Methylene chloride is the other name it's referenced as. Okay. Don't ask me to explain that nomenclature one. I still don't quite understand that. We're looking at a polar solvent because we have those electronegative chlorines, and it is aprotic because, again, we don't have a hydrogen bound to oxygen, nitrogen, or a halogen. Last one, acetic acid, polar protic. What if I told you benzoic acid? Do you need to see its structure? Why is benzoic acid polar protic? It's an acid. If it's an acid, by definition, it has a protic hydrogen. It has to be polar protic. Okay? Questions about your classifications? Kind of make sense? Okay. Sometimes you'll see these written out with structures. Sometimes you'll see them given as names. When it comes to exam 3, if I've written it out and I haven't given you the name, feel free to raise your hand and ask, and I will probably give it to you. When it comes to your final, you're going to have to know some of the more common ones. Okay, so these are good examples. Acetone's another good common one to have memorized. Structure of acetone, very, very similar to DMSO. Instead of a sulfoxide, you're looking at a carbonyl. Okay, so acetone is very standard to see written out. Okay, so I would recommend that you reference your textbook, look at some other lists of solvents so you're familiar with those. And Sarah? Yep. Okay. So the next part is looking at that secondary effect. Okay, what can it do to stabilize or destabilize reagents and intermediates? Okay, so we already kind of talked about this. What if we have a salt compound? What solvent would we want to use? So for instance, we dropped in sodium chloride. Okay, to get that salt to interact with everything else, what solvent should I use? I'm going to want something as polar as possible to help break that ionic bond so that it can actually get into solution so it can interact with things, which means probably the best solvent choice is going to be a polar protic. Okay? Depending on circumstances, we might have to shift to a polar aprotic, but under no circumstances would we use a nonpolar solvent, because the nonpolar solvent won't break that bond open, and we can't actually get access to the ions within it. Okay? Which type is going to stabilize a leaving group? It's a little bit trickier question. What is a leaving group? We can change our halogen phrase a little bit. Let's first deal with a leaving group. What's our leaving group going to do? It has to leave the structure, and by leaving the structure, what is it doing with the electrons? It takes them. So our leaving group is really going to be carrying what charge? A negative charge. What solvent's going to do a good job stabilizing that negative charge? Polar protic. So we might again expect a polar protic situation because we want to stabilize that negative as best as possible. Again, we could shift to a polar aprotic depending on our circumstances, but we wouldn't use that nonpolar solvent. Okay. Last one. Which type is bad for nucleophiles? What does our nucleophile have? A negative charge, at very least some source of electrons. What's going to be the worst solvent choice for a nucleophile? What do we want our nucleophile to do? It needs to be able to share its electrons with the substrate. Okay, so what's going to be the absolute worst choice for a nucleophile? For a solvent. The polar protic is the worst solvent. Okay, why?
Because it stabilizes at negative.
It's going to generate that H+, and what does that H+ then interact with? The negative of our nucleophile, taking that negative from a nice big strong negative to a neutral state. Is it as good of a nucleophile anymore? No. Why does this pose a problem? What was the best solvent for our salt compounds? Polar protic. What was the best solvent for our leaving group? And what's the worst solvent for our nucleophile? Polar protic. So if we have a situation where I have a nucleophile that I want to react, I don't want a polar protic solvent because it's going to ruin the nucleophile and it can't actually act anymore. Okay? So these secondary effects can do great things to stabilize intermediates, but they can also ruin them. So we have to kind of keep that in balance and in kind of the back of our head when we go through and process and evaluate each of these steps. Okay? Questions about any of that?
Does that mean polar aprotic's like the happy medium?
So our polar aprotic is very common when we're looking at individual reactions because it's kind of hits that middle ground. It doesn't make it so polar that it can neutralize our reactive intermediates, it's polar enough that it can stabilize our intermediates, but then not so polar that it destroys our reagents. Okay, so you typically do see the polar aprotic show up pretty much everywhere. Okay. That's not to say that we won't use the polar protic because it does play an important role. Okay. Next part of this is looking at our nucleophiles. This probably should have gone stepwise through because that's a lot of information up there. What do our nucleophiles do? They donate electrons. Okay. So what's going to be the first thing that you should look for in a nucleophile? Donatable electrons. Okay. What's a good thing to identify for donatable electrons? Negative charge, lone pair, pi bonds. Okay, you have to have those. If you don't have those, that atom is not going to act as a good nucleophile. Okay? So in the next step, we can then start to decide something about strength. Okay? If we have a negatively charged species, it will be stronger than the neutral counterpart. So we've got a couple examples there. Hydroxide versus water. Which one's the stronger nucleophile? Our hydroxide ends up being stronger because it has that negative charge. Where's that negative charge held? Why do you say the oxygen? That negative charge looks to be right next to the hydrogen. Thank you, general chemistry, for messing with our heads with charges. Okay? It's organic chemistry. Evaluate where your formal charges lie. This is why we went through and looked at Lewis structures. This is what's officially a formula. We have to interpret that formula into the proper Lewis structure and identify where those charges are located. Okay? Move to the next one. Hydrogen, I'm not even going to name that. HS minus versus H2S. Which is the better nucleophile?
HS minus.
HS minus. Okay? Last one. Or NH2 minus. So that was kind of easy, nice and straightforward. Okay, we got that negatively charged species, we can then work with it. But what if I compare the very first one and the very last one? Hydroxide to amide, OH minus to NH2 minus. They're both charged. How can I decide which one's the stronger nucleophile? We're going to have to move to a new rule. That new rule is what's in step 3. What we're looking at is how our nucleophilicity changes when we move from left to right on the periodic table. Okay, why only looking left to right? What if I looked up to down? Does the electronegativity change? Something else change? Size. When we look left to right, what did we say happened to size? Stayed effectively the same, so we can get away with just comparing our electronegativity. So when we're looking from left to right, and I'm always difficult with left to right, let's make sure we got this. Nucleophilicity decreases from left to right. So what we're saying is a fluoride is a worse nucleophile than oxide, worse nucleophile than amide. Okay, why might that be the case? Fluoride is more electronegative. It holds its electrons. So yes, it may have electrons, but is it willing to share them? No. No, and if it can't share them, it can't act as a nucleophile. Kind of makes sense? So, OH minus versus F minus. OH minus is the better nucleophile. NH3 to H2O? NH3 is our better nucleophile. So look, we can start to change both charge and its position on the periodic table. Notice that we will always try and compare them within an individual set. We won't see weird shifting all over the periodic table. Okay? After that, so those first 3 absolutely nailed down perfectly backwards, forwards, upside down. Okay? In a year from now, if I ask you to tell me which one's more nucleophilic, you should be able to tell me between fluoride and hydroxide. Okay? That's how ingrained into your head those first 3 rules need to be set. Okay? After that, it gets a lot more difficult to interpret, okay? Which is why the rest of them aren't boxed in red. What happens when we deal with size? So when we look within a row. Within a row, we have an electronegativity difference, but we also have a size difference. And we're trying to compare which one trumps, size or electronegativity. It usually comes back to size. So size is going to play a more important role when we deal with these, to a certain extent. What's that certain extent? It is dependent on the solvent used. All right, remember, your nucleophile in a polar protic solvent becomes weaker. So if I'm going to go through and start to compare size, I have to be aware of what's going on with the solvent. If I'm not specifying a solvent, then I'm looking at another, yet again, a new situation. Okay, so we have to be very careful with how we separate our nucleophilicity when it comes to size. So in a polar protic environment, what ends up happening is we're looking at the less electronegative atom being more nucleophilic. Why might that be the case? Should we see some pictures? I think the next slide has them. The more electronegative it is, what's it going to do in a polar protic environment? So if we compare chloride to bromide, do we have any electrons to look at when we're looking at electronegativity? There's no bonds, so we can't really look at that. What's going to happen in that polar protic solvent? So we go back to our rule. In the polar protic solvent, our less electronegative is more nucleophilic. Okay, so if we take a look at our polar protic solvent, which case is polar protic, top or bottom? The top one, what's the solvent being used in the top one? Water. So we're looking at our polar protic. I'm just going to say protic. Which one is our stronger nucleophile according to our rule? Cheap. Polar protic, less electronegative, more nucleophilic. Which one's our better nucleophile? Which one's less electronegative? Bromine. Which one's our better nucleophile? Bromine. So why is our bromine a better nucleophile? doesn't have to do with size in this case. It really does come back to electronegativity.
It's
No.
going to be a better. It's going to be a better leaving group, right? Because of the bonds between it.
It generates a stronger interaction with water when it's more electronegative. Okay. What does that stronger interaction end up doing?
Reduces its ability to.
Reduces its ability to actually be able to attack. We're not looking at leaving groups, we're looking at nucleophiles. So what we end up doing is creating a much stronger interaction with our positive ends of our water molecules. That stronger interaction requires more energy to break, which then does what to the strength of that nucleophile? Reduces it. It can't get out to actually attack. Bromine, being less electronegative and a larger dispersed electron cloud, doesn't interact as strongly with the water molecules. So it's not as difficult to break one of those water molecules away so that it can act as a nucleophile. Okay. What happens if we change our solvent? We go from a polar protic to a polar aprotic. Well, now in the aprotic situation, we can go back to a size argument, okay, which I tried to represent here as best I could. Okay. Chloride is smaller than bromine. Right, so now we aren't looking at a relatively strong interaction with our protic environment. We're looking at that aprotic system. We're going to see relatively weak interactions all the way around. But chloride is smaller. Why would that matter?
Because it can't stabilize its negative charge as well.
Which one was our stronger nucleophile, the chloride or the bromide? And a polar aprotic, smaller is more nucleophilic. So the chloride is more nucleophilic. Why does the chloride become more nucleophilic? We're now looking at the exact same types of interactions. Okay? In the hydrogen bonding solvent, we had a much stronger interaction because of that hydrogen bonding ability. Okay? When we shift into the aprotic environment, we're now looking at identical interactions around both of these. But what happens as I get bigger? There's more area, which means more solvent can interact. The more solvent molecules that are attached to our nucleophile, what do we have to do to have it act as a nucleophile? We have to break more of those interactions away before it can act as a nucleophile. So in the aprotic environment, the smaller our atom is, the more nucleophilic it becomes. Okay? And that's because we end up changing the level of interaction. With our hydrogen bonding solvent, that interaction is so much stronger that that's going to dominate our overall interpretation. When we move to the aprotic environment, our interactions get so much weaker that now really all we're concerned about is how much solvent is actually there, how much solvent has to get moved out of the way to allow it to react. Okay? Do you see this question show up every so often? It's fairly rare, okay? But I do want you to be aware of it. You're looking at opposite kind of interactions between these two. Okay? So the solvent dependence can change the ability of your nucleophile. The last one, if we have no solvent, the bigger one becomes more nucleophilic. Okay? And the term that usually gets floated around with that is more polarizable. It's so big that it can push its electron density wherever it wants, including into our substrate to form that new bond. Okay? So that solvent interaction, I would say, is probably the hardest one to worry about. At most, you're looking at one question on the test. And if you had this section memorized, or that bullet, number 4, memorized, you should be fine with that ranking system. Okay? Last one, steric hindrance. Steric hindrance is going to play actually a very large role when we move into Chapter 8 and we look at elimination reactions. Okay? It's also going to play a role when we look at our SN2 mechanisms. What steric hindrance is actually referring to is just electron bulk. The more electron density there is around an individual area, it tends to hinder that area from doing whatever it wants to. And why might it hinder it?
It's more difficult for the nucleophile to get to.
Yeah, our nucleophile has to get electrons out. If there's a bunch of electrons surrounding it, can it get the electrons out? No. Okay? So the less atoms we have around our nucleophile, the more nucleophilic it becomes. Why less atoms? What does an atom bring in? More electrons. So the less electrons around our nucleophile, the better off it becomes and the stronger that nucleophile becomes. All right? And here's where that becomes important. Okay? What does our nucleophile do? Donates electrons. And it donates those electrons to anything that's not hydrogen. Is there a competing species that donates electrons? Yeah. In fact, our Bronsted-Lowry bases donate electrons directly to hydrogen. Right, how is that going to be important for us? Well, if I want a nucleophile, do I want it to act as a base? No, it needs to act just as a nucleophile, because if it acts as a base, it's going to do other chemistry. Right, so if I want to run the substitution reaction, I really, really want it to only act as a nucleophile exclusively. Anything else, then I can get all sorts of other things getting in the way. So why does sterics play a role in this? Right, so if we take a look at a substrate and a nucleophile. First off, which one's which? Well, the one on the right was the substrate. How do you know that's the substrate? Because it has the leaving group of our halogen. How about the other species? The other species will be our nucleophile. How do we know it's going to act as the nucleophile? It has the negative charge. Okay? So here's another question. When we look at that nucleophile, which atom is the nucleophile? The oxygen. Which electrons on that oxygen, or associated with that oxygen, is the nucleophilic pair of electrons? The lone pair. Any one of the lone pairs. What happens to this bond between the oxygen and the carbon? Absolutely nothing. Do not change it. Okay? When we're going through and doing a reaction, what we're going to do is find our electrons and only move those electrons. So in this case, what we're saying is our nucleophile is going to share that pair of electrons with our carbon. Okay? Those of you in lab, can you help me out here? What kind of substrate do we have? Primary, secondary, tertiary? Tertiary. Would I expect the nucleophile to get in to be able to react with that substrate? Not really well. Why not? There's steric hindrance. Okay, so I might expect this reaction to run really, really slowly. Okay, but we could potentially get it to work. What happens if I switch it up and now drop this guy in there? Okay, what's going on with that new guy? Can it act as a nucleophile? Yeah, negatively charged. Got the lone pairs. Why not? It can go in and do the attack. Which of these two species would be the better nucleophile to attack that carbon? Left or right? The left one. Why? There's not as much junk in the way. That other junk is going to prevent that nucleophile from actually getting in and being able to attack. What does that species instead decide to react with? This is a mind-blowing thing here, maybe. Just so you know. Chapter 8. If it can't get in to that electrophilic carbon, it's going to go for the next most positive thing it can. It'll attack the hydrogen. Interesting. Why would it attack that hydrogen? How many bonds would that hydrogen then have?
Two.
Too many bonds, right? So what do we have to do? To break a bond, what bond do we break? So we take those electrons and we move them that direction. What happened then? Formed a pi bond, but then what's the problem? That carbon has too many electrons. Is there, say, an atom attached to that carbon with a very polar weak bond that can take the electrons away from that carbon?
Bromine.
The bromine. What type of reaction did I do? I did an elimination. What did my quote-unquote nucleophile act as in that situation? A base. It reacted with a hydrogen. So what we did was took our species that we would have predicted to act as a nucleophile, and instead it acts as a base. What happened on the other side? It could act as a nucleophile, and we could potentially see that substitution reaction. So depending on the nature of that negatively charged species, be it sterically big or sterically small, we can have it change its reactivity from a nucleophile to a base, or from a base to a nucleophile. So we have to be aware of those subtle changes and try and decide what conditions are going to best suit that overall reaction. Kind of a tricky and pseudo-neat concept. Questions on that? New structure. What do you think that species acts as? Pseudo hint. Let's give you, come on. So I've heard both answers, nucleophile and base. Look for the steric bulk. The steric bulk pushes it to act as a base, not as a nucleophile. This compound is used very typically solely as a base because it is sterically massive. When we look at the electron density or the groups attached to each of those nitrogens, there's so much electron density around there that it really can't get in to have those nitrogens act as nucleophiles. Okay, next question, because that one was too easy, right? Which lone pair is the basic lone pair? Red or blue? Whenever you're asked to evaluate which electrons are more reactive, there's something that you should immediately attempt to do. Resonance. I leave it to you to go through and draw all of your resonance options, but what you will find is there is only one option. You can take the red lone pair and move them down into that bond. So number one, I just said there's only one resonance option, and this is it, which means already which one's more nucleophilic, or sorry, basic? The blue, because the red's already doing resonance. The blue becomes even more basic. Why does it become more basic with this resonance option? Our carbon just picked up too many bonds, so we can move that pi bond now onto the nitrogen. What charge builds on that nitrogen? A negative charge. If it's negatively charged, we're now looking at it potentially acting as a base or a nucleophile. The sterics prevent it from acting as a nucleophile. We have an awesome base here. Okay. I wish I could tell you the name, but since none of you really know the structure, well, actually, since none of you know the structure, I can make up a name. The only thing I remember is the abbreviation, and I'm really only at a 50-50 option here. It's either DBU or DBN. Depends on the size of the ring. So DBN and DBU are both really good bases. Okay? They're both very similar to this structure. That ring on the left, depending on if it's got 7 or 8 atoms in it, I think it changes between DBN and DBU. DBN stands for that.
You were right, it is DBN.
Oh, sweet. Diazobicyclic
430 non-5-ene.
There you go. I'm not even going to say it. Okay. You're not going to be responsible for knowing the name for that. You are responsible for realizing that it is basic and which nitrogen is basic. Okay? Questions? Other questions other than naming?
Can you repeat why this one is more
Look at the resonance structures. When you look at your resonance structures, there is only one option to move electrons, and that's exactly what's being shown. So if we take a look at our red lone pair, we can move those electrons into the structure. If they move into the structure, can they react with a hydrogen? No. How about the blue electrons? I said there's only one resonance, and this is it. Those blue electrons cannot contribute to resonance, which means the only place for those blue electrons to go, out to hydrogen. So the blue electrons will act as your base. The red ones will actually contribute to the blue ones being more basic.
How come the blue ones can't shift to the right within the structure?
Since it's been asked twice, let's go ahead and do it. That's the wrong button. Let's try this button. No, that's the right button, but I'm not sure I'm going to be able to draw it well. And I'm just going to pretend that I've got it right. As long as I get the general structure, it'll be okay. Yeah, close enough. Red electrons, blue electrons. We said the red option, we came in to push it to there. And that puts that negative charge on that nitrogen. There's been a couple suggestions that we might be able to do something with those blue electrons. So let's take a look at those blue electrons. Diego, you want to run it by me again? What do you want to try? Move those electrons where? Right or left? To the. That's not what I wanted to do. To the right. How many bonds does this carbon have? It has 4 bonds prior to the electron motion. You move the electrons in. How many bonds does it have? 5. Does it have a weak polar bond that we can break to stabilize? In fact, since we're looking at resonance, does it have a pi bond? No. Which means where do the electrons move? Right back to that nitrogen. No resonance. Okay. You can run that same argument going the other direction as well. Okay. Questions? Remember how I said resonance was going to be important? Yeah. It's still going to be important. Common nucleophiles to watch out for. Pretty much any atom that you can put a negative charge on can work as a nucleophile. So you will see carbons as nucleophiles, though fairly rarely. Why would we see carbon as a rare nucleophile?
It's rarely negative.
It's very rarely negative. Why is it rarely negative?
It doesn't like to be negative.
Why does it not like to be negative? It's not very electronegative. Everything it's bound to has either the same electronegativity or greater than it, so it can't really steal electrons from that. There are some exceptions. I think we briefly talked about it with our triple bonds. Said the triple bond hydrogen could be a little bit acidic, so we could potentially pull that off to make that negative. Another option, which we'll see in second semester, what happens if I take a carbon and I bond it to a magnesium? What charge does the carbon become? Magnesium is a metal, which means it by definition is going to come out positive, which means the carbon is going to have to be negative. How do we know that? What type of bond is between magnesium and carbon? An ionic bond. So if one's positive, the other one's negative. Okay? So we've got a lot of options for our negatively charged nucleophiles. They gave you some examples here, but you can pretty much make any atom into a negatively charged nucleophile. The issue is just how you stabilize it. As far as your neutral nucleophiles go, water works pretty well. Your alcohol works fairly well. Why are those first two fairly similar as far as their nucleophilic strength? Does H bonding really have to do anything with the nucleophile? What's the nucleophile in both those cases? The oxygen. Why would we expect not much of a change in the nucleophilic strength between those two? What's the difference between those two structures?
Oh, hydrogen and carbon.
Hydrogen versus carbon, what's the difference in electronegativity?
Not much.
Virtually nothing. So we don't see a huge difference in nucleophilicity between those two. Your other neutral nucleophiles, you're looking at your nitrogens. Those end up being really, really good nucleophiles. We'll talk about those in second semester if you decide to stick through this. And then the last one, which very rarely will pop up, but you got to watch out for it just because sometimes I like to throw curveballs, is sulfur. How do we know sulfur might act as a nucleophile? Just having 2 bonds doesn't help me out. Where is sulfur on the periodic table? Underneath oxygen. What do you think about phosphorus? Could phosphorus act as a nucleophile?
Yeah,
Why?
because it's under nitrogen.
Underneath nitrogen. So they have the same overall Lewis structure, electron configurations. As long as we have that lone pair, we have the ability to share electrons. Why do we not look at a neutral chlorine? The only way we can get neutral chlorine is if we have Cl2 or halogens. So yeah, that's neutral. Would it act as a nucleophile? Why not? Already has its 1 bond. Can't act as a nucleophile. Okay? So your halides will only act as nucleophiles, which is kind of a nice little rule to throw in there. Okay? Because almost everything else could also act as a base. Why can your halides not act as bases? Nope. I won't accept that answer. I like the dissociate answer a little bit. What do you mean by that?
They're acids, they're not.
Let's take Br minus, react it with H plus. What do we get? We get HBr. What can you tell me about HBr?
Dissociation.
It's a strong acid, which by definition means it turns into the ions. We don't see our halogens act as bases because they immediately form strong acids and immediately spit the hydrogen, do the reverse reaction. Okay? So your halides are nice because they will only act as a nucleophile.
Does that change depending on what solvent is?
Nope. Okay, other questions? Shut up to the fun stuff. So, reaction mechanisms. Those of you in lab can help out and participate for those of you that aren't in lab. What we want to go through and do with every reaction, we're going to do it primarily for the substitution reactions, we'll do it for the elimination, and then probably try and do it for the addition and the radicals. I'm probably not going to do it for the radicals. I backstep on that one. Radicals are too ugly. Once you move into second semester, you should be thinking through the same kind of general logic and reasoning behind it, but you probably won't see a breakdown like this. So if we know this reaction works, what we now want to go through and do is determine how it worked or why it worked, so that when I change the conditions, I can predict those new products. So this is our observable. We need to come up with a hypothesis that we can then test in the lab. All right? So when we look at this reaction, what bonds were broken? What bonds were made? We broke the carbon iodide bond and we formed the carbon chlorine bond. Anything else happen? No, that's actually kind of nice. Okay. We can look at where the electrons moved, but ultimately it's still going back to we broke the bond and we made a bond. So there's really only 2 things that happened in this reaction. So how can we possibly organize those 2 things to predict how this reaction occurred? So we end up with 3 possible ways, right? What are those 3 possible ways?
All at the same time.
So we can have the bonds break and form simultaneously. Yes, I am writing it in very particular places. What else?
Break and then form.
We could break our bond first, then form, and our last possible option, we could form, then break. So all we're really trying to do is come up with all the possible ways that we can put this together. So we just have those 2 options. How can we possibly combine it? Think about coins. You get heads, 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 tails, and tails, head, tails, tails. Sorry. Okay. Before we push on into evaluating each of these, we might want to do a quick check over the top of them. Any one of these, absolutely impossible to work.
With 3.
Why does 3 not work? If we go back up to the drawing that I've already got there, if we decide to form the bond first, what we're saying is I'm going to put in a new bond between the carbon and the chlorine. So there's my new bond. I'm going to do that first. Carbon-chlorine bond. What's wrong with that structure? I only see 4 bonds, but you have to remember the implied hydrogens. If we erase that chlorine temporarily, there's 3 bonds shown, which means there is an implied hydrogen which did not change through the course of the reaction, so I can't remove it. If I'm going to form the bond first, how many bonds does that carbon now have? 5, which is impossible, despite all the research into it. Okay? And we should not even worry about mechanism 3. So what we want to go through and do is look at the basics of those first 2 options. I personally, for some reason, found the first option easier to interpret than the second option. So typically when I go through and talk about it, I'll start with that first one. Okay? Questions about how we came up with those 3 possibilities? Okay. This is a slightly different format in the way the textbook is going to present it. What you'll see in the textbook is, here's these 2 ways that this can happen. It either does this or it does this. Okay? They don't go through the reasoning behind how we even got to those 2 options. That's what we just did. Okay? Every mechanism is going through a similar process. Someone said, okay, what had to happen? Let's just write out the possible options and let's draw them all out. The exciting part of that, you draw it all out. So if you're ever trying to figure out an answer, what's the first thing you should do? Draw it all out. Okay? You'll notice sapling will have you draw things. Should you be drawing in sapling? Probably not. Why? You'll probably miss points because you'll end up doing it wrong. Okay? And that's because you aren't comfortable with drawing things within sapling. All digital images that get generated, they get drawn by hand first and they get converted into the digital image. Okay? And that's because we're much more comfortable with drawing by hand than we are with the digital images. Draw out your sapling homework. When they ask you to predict a product, draw the product on a piece of paper and convert it into the drawing for sapling so that you can get your credit correct. Evaluate each and every step. Make sure that you end up at a final neutral product. Okay? So, your SN1. Okay, we'll come back to that 1 meaning in a second. We want to break our carbon-iodine bond first, then form the carbon-chlorine. Glad I set this up stepwise so I can go through it all nice and easily. So, our first rule is to break the carbon-iodine bond. Where is the carbon-iodine bond? C2? Good, I like that answer. All right, then what are we going to do? We're going to break it. How is it going to break?
Iodine to take the electrons.
Why would iodine take the electrons from carbon? Iodine is more electronegative, so we're going to start the electrons in that bond, and we're going to show them going towards the iodine. All right. The result, what happened to the bond? It's gone. So we can now go through and draw in our iodine molecule. Where did the electrons in that bond go? Onto the iodine. Okay, so now that we've shown our Lewis structures of how the electrons move, before we can go on, we have to go back and finish drawing our Lewis structures. The last step of drawing Lewis structures, formal charges. 2 ways to approach this, or 3. Let's go with 3 ways. The worst way, in my opinion, you go through and you calculate the formal charge for every single atom. How do you calculate formal charge? Valence electrons minus the number of bonds minus the non-bonding electrons. Okay? That's the way I would recommend you go first. Any ideas why? Because then you get irritated and you learn how to do it so that you don't have to go through that long, tedious method. Okay? You'll find that your frustration level actually improves your grade as long as you continue to work. Okay? Second option Remember there was a table at the beginning of the semester. I said these are all the common bonding patterns that you will see with their particular charges. And I said this table is incredibly important. You should have it memorized so that when you get to something like reactions and mechanisms, it's not, oh, what's the formal charge? It's, oh, iodine doesn't have any bonds and it has 4 lone pairs. That means iodine needs to be negatively charged. Already there, no calculation, no thought, already done. Okay. Last method. Fourth method. Look at what happened to the structure. What was our overall charge? Neutral. What was the charge on the carbon atom? Neutral. What happened to it with that arrow? It lost electrons. So if we start with no charge and we lose a negative charge, electrons are negative, what happens to it? Its formal charge, it becomes positively charged. What happened to our iodine? Formally negative. Okay. Now that we've got these charges, or we've done one step, now what we should do with all mechanisms, is this the end? Okay. How do we know it's not the end? Okay. There's a 2 there, but let's say we get rid of that 2. How do we know this isn't the end? They're charged. Okay, we have too many charges in our structure. We need to stabilize those charges. Okay, so what happens now? Now we can bring in our chloride ion. What's that chloride ion going to do? I can accept the attack. I want a little bit different phrasing on that. It's going to share a pair of electrons with our positively charged carbon, and we end up with our final answer with our chlorine attached. Before we decide we're at our final answer, what do we have to evaluate? Charges. Are our charges appropriate? Carbon started positive, gained electrons, so it became neutral. Our chloride started negative, lost electrons, so it's now neutral as well. Okay. What we now have set up here is our overall mechanism. Nice and stepwise drawn out. So let's take a look at a fancier version of this with a little bit more detail. You'll notice that the one that I just drew up only had 2 steps. This one has 3. Why does it have 3? We've added a little bit more detail to this. Okay? That detail has to do with the nucleophile. And that previous reaction, what was our nucleophile? Chlorine, or rather chloride. Does it have a hydrogen attached to it? No. So when the chloride goes in, shares its electrons, do I have a hydrogen to get rid of in the next step? No. So I don't have to worry about it. Okay, we were able to stop it after just those first 2 steps. Okay. One of the issues, or one of the extra pieces of information brought in with this mechanism, is starting to look at and evaluate some of the characteristics of this. If we look at our reaction, okay, let's focus on just this. Well, actually, before we do that, what's the last step? What happened to the structure? It's giving up a hydrogen. So the only thing that changed was the location of a hydrogen ion, which means what type of reaction occurred? Acid-base reaction. You should be comfortable with that step of the reaction, regardless of if it happens before or after the substitution. You're still responsible for that, and that's starting to get strung in there. So depending on the level of difficulty, you might see that external or that optional step. Okay. How would you know you need to do it? I could accept that when the hydrogen's there. What else?
Something to do with that red circle.
If your product is not neutral, you need to fix that. Okay, so it's going to continue to fix itself or adjust its charges to get rid of that charge. In this case, the easiest bond or the easiest place to get electrons from is that hydrogen. Okay? So let's look at our substitution reaction. Okay? We've got two steps, our mechanistic step 1 and mechanistic step 2. Of those two steps, which is the slowest step? Why is step 1 slower than step 2?
Because breaks a bond, that's it. Step 2 has charges in it.
You're breaking a bond, we're generating charges. We started neutral, we generate charges, we're going up in energy. If we look officially at that last step or that next step, and if we ignore that we have to deal with that hydrogen, what charge would our nucleophile be? If we ignore the hydrogen, it'd be neutral, right? So it would have transitioned from a charged state to a neutral state. What happens to the overall energy? Goes down. So we might predict that that very first step is actually going to be the hardest step in this mechanism. Right? We're looking at two fairly large atoms separating away from each other. If that is the slowest step, what can we then do? Involving maybe the letter R, but not resonance. We can look at a rate law. Figure out something about the speed of this reaction. Think back to 152. What is our rate dependent on? In the rate determining step. The slow step of the reaction is what's going to determine your rate. So it'll be rate equals our rate constant times the concentration of our reactants in the rate determining step. If that rate determining step is our first one, our RDS, what are our reactants in that first step? It is just the substrate. What's the order of this reaction? First order. What mechanism do we call this? SN1. What's the 1 coming from? Has to do with the order of the reaction. The other phrasing that can come into this is the molecularity of the reaction. This is a unimolecular reaction, meaning when we look at our rate or our rate expression, there is only one reactant in that rate expression. Every other step happens so fast, we don't have to evaluate any of the reagents in those steps. So in the SN1 reaction, the only thing that I care about is the substrate. I don't care about the strength of the nucleophile or anything else. How does that show up in our reaction? If we think back to the general form of this, what did I have? I had M/H. Why does this only show H and not M? If it was M, what happens to the nucleophile? M stood for metal. We had an ionic bond, and our nucleophile was negatively charged, meaning the nucleophile was strong. In this case, do I want a strong nucleophile? Or rather, do I need one? Nope. If I don't need to use a strong reagent, I'm not going to use it because I don't want it doing something else in the reaction or potentially burning me. So when we go through and look at our choices, we're going to make sure that the nucleophile we use is relatively weak. So we'll be looking at neutral nucleophiles when we look at the SN1 reaction. Okay? So the nucleophile becomes irrelevant in our conversation. What else becomes important? We're really just concerned about the substrate. For this reaction to work, what has to happen? We have to have the leaving group take the electrons away from the substrate. And we address leaving group ability. It has to be electronegative so it can take the electrons. And we didn't touch so much on the substrate, and that's because depending on the mechanism, that substrate may or may not matter. For the leaving group to leave, it must hold the electrons, but then the other part, the counter ion, must also be stable. If that positive charge is not stable on its own, can the leaving group leave? No. If the leaving group never leaves, can the nucleophile ever attack? No, which means no reaction. So the primary thing I'm concerned about when I look at an SN1 reaction is I must form a stable carbocation. Okay? So when you look at the substrate, you have to decide, yes, that is a stable carbocation, or that can form a stable carbocation. If it can, SN1 mechanism. Okay? Does it matter which mechanism? Yep, it actually does. What if we started with a stereocenter? Okay, let's say there's 4 different things attached to that substrate where the leaving group was. Okay. If we look at the product, I guess I got to add a bond there instead of just kind of vaguely mentioning it. There's an extra bond. So now we have a stereocenter. If we look at the product, we'd still have that bond there. So we'd still have a stereocenter. In the course of the reaction, would I expect the exact same stereocenter or a different one? What happens in the very first step of this mechanism? The leaving group leaves. Do we have a stereocenter anymore? No. What we've got left is a positive charge. Where's that positive charge located? In a p orbital that has 2 lobes. One above the plane and one below the plane. Where can the nucleophile dump its electrons? Either or, which means we end up with both stereocenters as a possibility. So depending on how the reaction works, we can get different products. So you absolutely must be super confident in being able to identify, yes, that is an SN1 or that is not SN1, at least at this point. Okay? So this is our overall reaction. Like I said already, primary thing we're concerned about is the stability of the carbocation. We still need a good leaving group, but every substitution reaction is going to need that. So it's really focused in on that leaving group, or sorry, your substrate stability.
Does that mean that you get enantiomers after
Yes.
that happens if you have both?
Exactly right. Way to tie it all back together. We'll come back to it too. So. Questions on this? Let's see, where do I push? So there's our rate law again. Rate times our K times our substrate. Oh, here we go. In the formation of our carbocation, which of these carbocations was the most stable? Top or bottom? Bottom. What kind of carbocation do we have here? Tertiary carbocation. Why is the tertiary carbocation more stable? There's more carbons around that carbocation in the center. What does that do for us? Carbon has more electrons than the hydrogen, and we have more electron density to stabilize that carbocation. We end up with a more likely product. So if we go through and look at an SN1 reaction, which of these substrates would we expect to react the fastest? The tertiary, because it makes that stable carbocation. Okay? Kind of makes sense? Oh, there we go, most stable. So what about the following alkyl halides? Should they react according to an SN1 reaction? That very first one, primary, secondary, or tertiary? Primary. Would we expect it to react?
Yeah, because it has resonance.
What we've addressed so far is just this primary, secondary, tertiary ability. Is there something else that we could do to stabilize a positive charge? We can do resonance. Resonance will come back with a vengeance with the SN1 mechanisms. Okay? If we take a look at our first intermediate structure, what's the result? I can now show resonance shifting the pi electron density over to that other carbon. What happens to the charge on that far right carbon? The far right carbon actually has less positive charge, which means we have now stabilized it. Okay? The very last one on that list also will allow for resonance stabilization within that ring. That middle one, there is no resonance ability on that. That one becomes very, very tricky to go through and see. I'm going to draw that, but then I'll end with it. What is the hybridization of the carbocation carbon? Of the carbocation carbon. It is sp hybridized. For it to be sp hybridized, there has to be 2 p orbitals left over that have not reacted. One is contributing to the pi system, okay, all the double bonds. What's the other one doing? That's our carbocation. If we have two p orbitals, can they both be parallel to each other on the same atom? No, they must be perpendicular. If our orbitals are perpendicular, can we do resonance? No, they must be parallel. They have to be aligned with each other. That carbocation is not resonance stabilized. Okay? Very tricky one to pick out and see. Sorry about that, but I will stop.